Nice. In this lecture, we are going to study this function. So we are given the function f of x equal to the log of absolute value of x divided by log square of absolute value of x minus log of x plus 1. So you have the function f of x equal to the log of the absolute value of x divided by log square of absolute value of x plus log of absolute value of x minus terms. Please let me get my earphones. Okay, nice. Excuse me, I am back. So here we were saying that the function is not it is minus. So let's cancel this part and put minus and plus 1, right? So as usual, the first question is find the domain, possible asymptotes, possible symmetrics, and asymptote show that f admits a continued prolongation in x equals 0, right? So we need to find the domain, find possible symmetrics and asymptotes show that f admits a continued prolongation. Okay, let's make it big. In our case, as usual, we have two conditions for the domain. We have logarithm of absolute value of quantity, right? And when one has logarithm and you have logarithm of absolute value of quantity, the condition for the domain is that the quantity should not be equal to 0. So in this case, we have logarithm of absolute value of x, so we just make x not equal to 0. Then we have a denominator that we write down that denominator log of absolute value of x squared plus log minus the log of absolute value of x plus 1 should be different than 0. So these are my two conditions. The first condition is easy, as it meant that x should not be equal to 0. Now second condition, how to solve it? To solve it, I can set big X equal to log of absolute value of x, right? Such that this become big X squared minus big X plus 1 should not be equal to. Is that clear? When this is done, we turn back to x not equal to 0, and how do I solve this? By using the delta. I do the delta, which is the discriminant, equal to minus 1 square minus 4 into 1 time 1. So give you 1 minus 4 equal to minus 3. As the delta here is negative, there is no solution, right? So when the delta is negative, there is no solution. This means that this stuff can never be equal to 0, right? And so this condition holds for all x belonging to R, right? The condition holds for all x belonging to R. So it's this stuff here can never give 0 as the determinant is negative. Okay? So we remain as the only condition for the domain is that x is different than 0. So the domain of f will be from minus infinity to 0, union 0 to plus infinity. Okay. Now, what do you observe when you look at the function? You see the absolute value everywhere, right? It means that if you try to do, so I am talking about symmetries, the symmetries. If you do f of x, if you do f of minus x, this will give you the logarithm of the absolute value of minus x divided by the log square of absolute value of minus x minus the log of absolute value of minus x plus 1. But this, you remember that the absolute value of minus x is the absolute value of x. So it just gives you log of absolute value of x divided by log of log square of absolute value of x minus log of absolute value of x plus 1. That is equal to f of x. What have I proved? I proved that f of minus x is f of x. So we say that f is even, right? F is an even function. F is an even function. What happens if the function is even? When the function is even, you can just study it. Okay, if your function is even, the graph of the function is symmetric, okay, with respect to the y-axis. Okay, this means that the graph of the function is symmetric with respect to the y-axis. Is that clear? Nice. As the graph of the function is symmetric with respect to the x-axis, what does it mean? What does this mean? So let's try to understand what is the implication of this. If I know that the graph of a function is symmetric with respect to the x-axis, suppose that I have this function. If I know that this function is even, to the other parts, the graph will just be like this. Yes or not? This is what means symmetric with respect to the this is the y-axis, right? It's like a mirror. So the y-axis is a kind of like when you see yourself inside a glass. Exactly like that. So when you know that your function is even, you can just study it for the part where x is greater than 0. This because the other part, you will just deduce the other part. You see, once I know the blue part, I can just deduce the black part. But even if you didn't notice this, it's not important. You just study the function as usual. But if you note it, it makes your life easier, right? In the sense that instead of doing many stuff, you just do. Yes or not? Is that clear? Now, as we know, so we are going we are going to study f only for all x greater than 0. I repeat, you can study it as usual, no problem. It doesn't change anything. Okay? But if you notice this makes your life easier. Now, when x is, I repeat you that absolute value of x is exactly equal to x if x is greater than 0, right? So for x greater than 0, the function f of x will become what? Just the log of x divided by log square of x minus log of x. This is log square plus 1. Yes or not? Now we can find, I am not, when we notice that it is even, but when you find the limits, you will deduce the order. For example, I remind you that the domain was from minus infinity to 0 union 0 to plus infinity, right? When the function is even, look, what happened? The thing that happened at plus infinity, it happened the same at minus infinity. Okay, so I just need to compute the limit here, and I have done. Okay, so so what is the limit? So I'm saying, what is the limit of f of x when x tends to 0 plus? If I substitute 0 plus in the function, you can easily see that you will get logarithm of 0, which is infinity, right? So up, I mean, if you put 0, let's put it, you will get log of 0 divided by log square of 0 plus a minus times log of 0 plus 1, right? At this point, so this is a minus. At this point, note that the log square of 0, so this means what? It means infinity over infinity, right? But here, the most important infinity is the log square. Yes or not? At up, there is only one infinity, so we get infinity divided by, it's like getting, like you have log square of 0, log of 0 up, but below you have log square of 0. This means 1 over log of 0. Yes or not? That means 1 over minus infinity, that is equal to 0. Doubts? Yes, it's minus infinity. Because I have log and I have log square. So the question of my student is, how did I get 1? Because I have log at the numerator and log square at the denominator, so I simplify the log. Doubts? Because I keep in mind that log square of 0 means log of 0 multiplied by log of 0. Okay. Now we got the limit at 0 plus so it's clear that as the limit at the limit when x tends to 0 minus would also be exactly 0 0. Yes or not? This is due to the fact that the function is even. Now let's do the limit of f of x when x tends to plus infinity. It's the same. The function at up you will just get log of x, right? Down you will get log square of x. Once more it will be 1 over log of x. It will be 0. So we deduce that from this, as the function is even, the limit when x tends to minus infinity would also be 0. Now the asymptotes we just have let's say, do you have vertical asymptote? The answer is no. because there is no point where the function go to infinity. Yes or not? There is no point where the function go to infinity. Do we have horizontal asymptote? The answer is yes. And the equation of the horizontal asymptote is y equal to 0, right? This for plus infinity and minus infinity. Because I repeat, to have the horizontal asymptote, the limit when the function tends to plus infinity or minus infinity should give a number. In this case, we got that that limit was 0, and so the horizontal asymptote is y equal to 0. Nice. Let's go back to the stuff. This solves the first. No, we still have to analyze that we have continued prolongation at 0. Okay, so continue prolongation. I remind you that I told you last time that in a previous exercise that if f is not defined, so if f is not defined at some point x0, but the limit when x tends to x0 of f of x, when x tends to x0 minus of f of x is the same as the limit when x tends to x0 of f of x, this is x0 plus. So if the limit from the left and the limit from the right are the same and they are equal to some number, let's say L, then we say that f admits a continuous prolongation. F admits a continued prolongation at x0. So the condition to admit a continued prolongation software is that first, the function should not be defined at that point. Second, the limit from the left and the right should be the same. The exercise asks us to prove that this function here admits the continued prolongation at 0. Let's check the first condition. Yes, f is not defined at x equal. F is not defined at x equal to 0. Yes or not? The function that they gave us is not defined at the point 0. This meets the first condition. Second condition, when we did the limit when x tends to 0 plus of f of x, we saw that it gave the same as the limit when x tends to 0 minus of f of x, and it gave of 0, right? So both the condition to admit the continued prolongation are met. So the first one is that the function is not defined at the point, and the second one is that the limit from the left and the limit from the right are the same. This means that f admits a continued prolongation at x equals 0. Okay, and what is such continued prolongation? Such a continued prolongation can be written like g of x equal to exactly f of x is equal to f of x, okay, when x is not 0, and it is equal to 0 when x is equal to 0, because the common limit gave 0. Is that clear? Nice. So next question. Then denote the continued prolongation by g, as we did. Compute the derivative. Find the differentiable point of g and specify the type of this not differentiable points. Okay. So we need to find down the derivative. Excuse me. I don't know what I touches here. Close. Okay. So let me take a new page on which we'll compute the derivative. Okay. So the function was f of x equal to, I told you that we will just refer on the positive part, right? And then because the function is even, So let's go and find but normally we are they say find the use g of x. But what is g of x? They say we saw that, excuse me, that let me, so g of x is this function, this for x not equal to 0, right? Let's say this for x greater than 0, and it is 0 when x is equal to. So what is g prime of x? G prime of x is only the derivative of, so the derivative of 0 is 0, so we don't care. The derivative of log of x, so this derivative here, we will use the rule of the quotient rule. Let's say if you have u divided by v, the derivative of this is u prime v minus v prime u divided by v square, right? So going back, what is u is log of x, v is all this stuff at the denominator. So we'll have 1 over x multiplied by the log square of x minus the log of x plus 1 minus, now we derive the one at the denominator, that will give of 2 the derivative of this guy here. I repeat that the formula is that if you have u to power n, the formula is n times u prime times u to power n minus 1, right? So the formula of log square will be 2 multiplied by u prime, which is 1 over x, so it will give you 2 over x, multiplied by u, which is log of x, to the power 2 minus 1, so it gives you like this. No, but I'm supposed to write it up. So I was saying that it will give let's put 2 over x log of x yes, minus 1 over x, yes, plus 0, that we multiply by log of x, right? Now all this will be divided by log square of x plus log, minus log of x plus 1 all square. Okay, then next step, we says that g prime of x, excuse me, let me write it better. G prime of x is equal to the 0 below. Now we expand this, so I will get a log x over x, right? Log x over x, log square x over x times, then minus log x over x, then plus 1 over x, then minus 2 log square, like minus 2 log square x over x, minus log x over x. All this over, let me just write the denominator square, right? I mean this denominator. That's, let me even, so let's just say the denominator, and the denominator is all this stuff. So we get g prime, I don't know why I keep empty, right? G prime of x equal to what? Okay, because we have, yes, 1 minus log square of x over x minus 2 log x over x, okay, plus 1 over x, all divided by the denominator. Okay, now g prime of x, okay, there is also the 0. This is when x is greater than 0 and when x is not when x is equal to 0. So g of x at the end give you g prime of x, I mean, we can factor out 1 over x, right? You agree? I mean, it will become 1 over x, factor of minus log square of x. Let me take it out. Let me take minus 1 over x out, so it will become log square of x plus 2 log of x minus 1, all divided by the denominator, right? And 0. I like to write it like this, but if you are at the exam and you don't want, you can write it like, just because I dislike to have fraction at the numerator, so I like to write it like like log square of x plus 2 log of x minus 1 over x multiplied by the denominator. Okay, this 0. Okay, so here is our derivative. Any question? Now when one look at this derivative, this is when x is greater than 0 and this one is x equal. When you look at this derivative, your question, you see that the point where the function may not be differentiable is 0, right? Because 0 is the point that may make this denominator go to 0. So we go and study the limit when x tends to 0 of g prime of x, because they tell us to study not differentiable points, right? How do I know that I should study at 0? Because I'm saying that here, if I put 0, the denominator may go to 0, right? And so that the function may go to, the derivative may go to infinity. So let's go and study. If we put this gives us 2 log square of 0. Log square of 0 plus 2 log of 0 minus 1 over okay, it is 0 multiplied by the denominator, that was what? Log square x minus 0. Yeah, so this is 0 plus 1. Okay, so this is the situation we have. Let's try to simplify. So basically at the numerator, these are all infinities, right? Because this is going to minus, this is going to infinity, this to infinity, and this is a number. So we take the most important one, this one, right? So getting log square of 0 at the numerator. Now below we have 0 time. Here we can also take the most important one. Okay, square, thank you. So it will become log 4 of 0, right? That's the most important one, because this square, when you square it, becomes log to power 4. Is that clear for all of you? Is that clear for you? Is it clear? Okay. I smile a bit. So okay, so it's 1 over 0 multiplied by the log square right? But at this point, remember that this is so like you have 0 here. This I taught you last time that instead of this is this 0 come from x, right? It comes from this x. So anytime you have x multiplied by the log of x when x tends to 0, this guy will tend to 0, this guy will tend to infinity, but the total result will be 0 because polynomials are stronger than logarithms. Is that clear? So by the end, even if this was 0 times infinity, we get 1 over 0, that is infinity, right? I don't care which kind of infinity is it. I don't know if it is but yeah, this is 0 times plus infinity. I mean, if we are doing, no, it's not that I don't care which kind of 0 is it. It's important because we need to know the type of the point. So here, if we are doing the limit, so it's 1 over 0. This means that if we are doing the limit at 0 minus, here it will be 1 over 0 minus and give you minus infinity. If you are doing at 0 plus, it will be 1 over 0 plus and give you plus infinity. When the points give different infinities from one side to another, how do you so the function wants, so we say first of all that g is not differentiable at x equal to 0. This is what we say. But when the derivative give plus infinity to one side and minus infinity to the other side, the point is, we say that x equal to 0 is a cups point. Okay, it's a cups. Yes. Doubts? A short review of this could be the following. Yes. Okay, a short review of this can be the following. Is the following. So x equal to 0 is so if you do the derivative, and the derivative, if the derivative from the left give a number and the derivative from the right give a different number, then these are two numbers. You said that you have a corner point, right? But if the derivative from the left give plus infinity, the derivative from the right give minus infinity, so or vice versa, it is a cups. If the derivative from the right they both give plus infinity and minus infinity, or they both if they have this, I mean, they both give plus infinity or they both give minus infinity, you have a vertical tangent point. A vertical tangent point. Right give also plus infinity. If they both give plus infinity or they both give minus infinity, you have a vertical tangent point. Okay? Nice. So we computed our derivative. We studied the point of not differential where the function is not differentiable. Now we continue by find monotonicity interval of g and minimum maximum, and saying if there are local or global minimum. So we need to find to study the monotonicity of the function. Maybe it's better to copy the derivative and take a new page. Oh, excuse me. Here is the derivative was here. Okay, so it is log square of x plus 2 log of x minus 1 over x times the denominator. So it is okay, and says that the derivative was g prime of x equal to log square of x plus 2 log of x minus 1 over x. Excuse me, can you repeat please? Yes, so it is minus x multiplied by the denominator, right? Yes, it was minus 1 over x times. Is there any question? So I repeat what my student subject my student just remind me that we took 1 over minus 1 over x outside, so it wasn't 1 over x. That's why we have this minus here, and the denominator is what we had in the previous board. Now we want to study the sign of this stuff. It's clear that the denominator, as it is something square, it's always the d is always greater than 0, right? So for this part we don't care because it's always greater than 0. We just need to study the sign of minus x and the sign of log square of x plus 2 log of x minus 1. So let's start, but for the x is easy. We can minus x is greater than 0. It means that when x is smaller than 0, right? Now we need to find where log square, let's go back and say log square of x plus 2 log of x minus 1 is greater than 0. We need to solve this. Once more, we set big X equal to log of x, and thus we get the equation x squared plus 2 big X minus 1 greater than 0. To solve this, we need to find the root. Delta equal to, it will be 4 minus 4 times 1 times minus 1, that is going to be 8, right? So the roots are big X equal to minus 2 plus or minus, these are x1 x2, root of 8 divided by 2, right? That means minus 2 plus or minus 2 root 2, because root of a is 2 root 2 divided by 2. We can simplify the 2 and we get, you see how we can, it's easy to see that this can be written like 2 multiplied by, let's say 2 multiplied by minus 1 plus or minus root 2 divided by 2. So it leads to minus 1 plus or minus root 2. These are my x1 and 2. Okay, now is there any question? If I have x1 equal to minus 1 minus root 2, it means that the logarithm of x is minus 1 minus root 2, and thus we apply the exponential to both the sides. When we reach here, we apply exponential here and exponential here. If you do exponential logarithm of x, I get x. So x is exponential of minus, let me write it like this, is the sum. Okay, to the other side, we get that x2 is minus 1 plus root 2. So getting that the logarithm of x is minus 1 plus root 2, and applying the exponential, we get x equal to exponential of minus, if I factor out the minus, I get 1 minus root 2, right? Okay, so these are the roots x1 and x2. Given that you have that x1 is here, x2 is here, we are studying the sign of a parabola, right? Because this look like a parabola. So it will behave like, yes or not? Because the part with x squared is positive. Then this means that here it is positive, then here it is positive, because it is above the x-axis. but here in between is negative. Now we are able to do our table because we know where each stuff are positive and where they are negative. Remember, the table, the first line of the table is all the domain. So here is x, so we made from minus infinity, 0, plus infinity. Nice. You can see that both x1 and x2 are positive, right? So we put x1 here and x2 here. No, are we sure? Yes, x1 is smaller than x2. Okay. Then I need to put the first component is minus x. The second component is exponential, is let me call it just the numerator. Okay, let me write it. So log square of x plus 2 log x minus 1, and then finally the denominator, the d, and here we get f prime. So from this, now we split, but for the moment I will keep this part like this, just for the moment, because remember that we were studying the function only from 0 to plus infinity, right? Because it was even. So we saw that this function here, minus x, we study it here. When we say minus x is greater than 0 only when x is smaller than z. Okay, so here, as we in this interval, it will be always negative. Is that clear? Because this function here is greater than 0 only when x is smaller than 0, but here s is bigger than 0. Okay, now this one, we saw that this one here, we saw that in between x1 and x2 it's negative, but outside it is positive. So here it is negative, but here it is positive. Then this function, the denominator here is always positive. So at the end we get that the sign of the derivative is going to be minus, plus, and minus. Now look, we need to translate this sign of the derivative by symmetry, using our symmetry, because what is this? This is like the y-axis, right? This here, it is the y-axis. So we use the fact that the function is symmetric to transfer it to this side. First of all, if the y-axis is like a glass, you will see all the point x1 and x2 will come here and be minus x1 and minus x2. Is that clear? Then you will split and split. Okay, now pay attention. Look, what happened is going to be the contrary. Look, when this stuff, when you say that something is increasing here, what happens to its image? So when something is increasing to one side, to the other side it will be decreasing. Is that clear? Doubts? Is that clear of this? So here, to sign up the stop due to the symmetry, in this interval that is minus, here it will be, where it's plus, here it will be minus, and here it will be minus will become plus. Okay, doubts? So this is, now I don't, basically look, it will means that you need to do to study the sign of here. I don't need to put anything here. Okay, it's okay. So you end up by saying that the function is positive. Let's say you can now say, you know, from this that f, you will say that f is increasing in, and f is, for example, let's write for f is increasing in minus infinity till minus x1, I mean minus x2, right, in this interval. Then in this one, the comma, from minus x1 to 0, and from x1 to x2. These are the interval where the function is increasing. And you know how the other interval are the interval where the function is decreasing. Now let's do the other table. Let's do the table that summarize all to rate maximum and minimum. So in this table that summarize all, we just have the derivative and the function, right? So it will be minus infinity minus x2 minus x1 0 x1 x2 and plus infinity. In this table, we have it was plus minus plus minus plus minus plus minus plus minus plus minus. Nice. Then so at plus infinity, at minus infinity, I think the limit was 0, right? Yes. So the function start here, increase to f of x1. So f of minus x2, I mean this is minus x2. Doubts? Then here it decrease to f of minus x1. Then increase again to f of 0. Then we don't care, because by the way we say that the function is defined at 0 and that the image of 0 is 0. Is that clear? Here, please, I repeat the question of my student. Typically, I used to tell you that if the function is not defined somewhere, put 2 bars. But here, we are studying the continued prolongation, in which we say that f of 0 is 0. So we don't need to put 2 bars, because here we say that the image of 0 is 0. Is that clear? Can you hear me, please? Okay. So then the function will decrease again. Will decrease again from here to it will decrease again from here to to f of x1, and then increase to f of x2, and finally decrease to, yes or not, f of to 0. Okay. So here is the function. So what we need to do is to have an estimation of what is f of minus x1 and f of minus x2. But if you have a look, the function, I tell you that the function was f of x equal to, it was what already? Log of the modulus of x divided by log square modulus of x. Okay. Thus, if x1 is exponential of minus 1 plus root 2, and x2 is exponential of minus 1 minus root 2. So So if we substitute, just to have a rough idea about what is the if you substitute, it gives you the logarithm of exponential of because, by the way, I don't need the absolute value because these numbers are positive. Exponential of 1 minus 1 plus root 2 divided by the logarithm of logarithm square of exponential of minus 1 plus root 2 minus the logarithm of exponential of minus 1 plus root 2 plus 1. So it basically gives you, at the numerator you will just get minus 1 plus root 2, right, divided by, here you get minus 1, it will be minus 1 plus root 2 all square minus 1, it will be plus 1 plus root 2, right, and plus 1. Yes or not? You see that this is a negative number. For me, what is important is just to know that it's positive or negative number. All this stuff is positive, but the numerator is negative, so it leads to a negative number. It's smaller than 0. So I don't want to compute exactly. So we saw that f of x1 is smaller than 0. Now for f of x2, we can do the same, right? But f of x2 is here. We can just see that f of x2 is above 0, right? Because from f of x2 we decrease to 0, so it is a positive number. You don't need to compute it. In fact, the graphs, they say compute a qualitative graph. Qualitative. Okay? So you see that this guy here is negative, smaller than 0, and it is the same as this guy because the function is even, right? F of x1 will be the same as f of minus x1. So to draw the graph, you basically have your 0, you have x1, you have x2, you have minus x1 and minus x2. Is that clear? Then okay, you have that the function at minus infinity is 0. Look, the function you have the points minus infinity 0, and then you will increase. So let's first put f of, we saw that the image of this point is positive, so we saw that the image of x2 is positive, so it is somewhere, let me put it in black, it is somewhere here. So also the one of minus x2 will be the same. Doubts? Then we saw that let me even concentrate only on the positive part. The image of x1 is negative, right? Like this, and that the image of 0 is 0. We saw that when the function tends to infinity, the function goes to 0. So to represent the positive part, what do we have? We have a function that stands here, decrease, then go to this, and finally come like this. Okay? Remember that 0 was a not differentiable point. So you need to make sure that you let me make it, the tangent line to the function at 0 should be mamma mia. Okay, by the way, so it was, let me I will it's better to use a smaller arrays so that. Okay, so let's draw. So remember that at 0 the tangent line was vertical, right? It means that the graph goes something like this. You got it? And then go, it's very vertical. Is that clear? Cups. Yes, cups, excuse me. Yes, it's a cups. No, even the cups is the same. So the cups is like, it's vertical, but from one side it is decreasing and to the other side it is increasing. Okay, excuse me. So yes, my student just repeat that, remind me that it was a cups. So yes, it's a cups. So then how do you draw the graph to the other side? It will be exactly the image of what you did. The image, the exact image. Like you take it here like this, go like this, then it goes up, and okay, and this plot your function. Any question? Then the last question says, draw g of x equal to no. Okay, find the solution of g of x equal to 1. So we want to solve g of x equal to 1. The question is that we should know this value, but I remind you that this function is g of x2, right? What does it mean? It means that if this g of x2 is greater than 1, because to do that, it's just according, we just need to know if 1 is here or below. Because if 1 is below, there will be 4 solutions. But if 1 is up, there will be. So the question is find the number of solutions or to find the solution. Find the solutions, not the number of solutions. So we need to solve it. So we don't even need to go back on the graph. We need to solve it. If it was number of solution, we'll have it. So we need to solve g of x equal to 1, right? It means that we will solve what is the, it's the stuff, it's logarithm of absolute value of x divided by log square of absolute value of x minus the log of absolute value of x. Thus you can just I'm coming, just try, I just attach the PC because it's not how to. Okay, so this leads to what, to which equation? It leads to the equation log square of absolute value of x minus log of absolute value of x plus 1 equal to log of absolute value of x, right? normally look, before doing this, if you have an equation, before doing what I did now, you need to check if this stuff is different than 0 to make sense. But indeed, we already checked it before. We saw that it will never be equal to 0. You need to check if it is equal to 0 and exclude those x from the possible solutions. So this leads to the equation log of absolute value of x minus 2 log of absolute value of x plus 1 equal to 0, right? And you set big log square, big X equal to log of absolute value of x. As usual, you get x squared minus 2x plus 1 equal to 0, right? But this is like x minus 1 square equal to 0. That's big X is just equal to 1. As big X is 1, we get that logarithm of absolute value of x is equal to 1. We apply the exponential and we get exponential of x is equal to e. So x is plus or minus e. Okay, this solve this question. Okay, and this is the end of this recording section. We continue in the next video.